Hello, in this video we're going to look at the birthday problem slash paradox. Some people call it the birthday paradox, some call it the birthday problem. And essentially what it is we're going to look at the probability that at least two people have the same birthday out of a sample of size n. And in here we'll assume that there's 365 days a year, so we'll ignore leap year, and each day it's equally likely. Now there are, dozens and dozens of videos on this topic, and so what we want to do in this video is to solve it in a unique way. And unique doesn't mean that it's original, it just means that I haven't seen it solved this way out there, and I think it's educational. So if you're wanting to become better at combinations, permutations, combinatorics, that type of area, then this is an educational video for you. And when you're dealing with combinations, permutations, it can be a little bit tedious, but stay with me and we'll work our way through this video. There's 3 pages. So in notation, we're going to let capital N be the sample size. And so the notorious, how large a sample do you need for it to be greater than the flip of a coin that at least 2 people have the same birthday? And the answer is 23, which seems so counterintuitive, and that's kind of why they call it a paradox. But we're going to let Y equal the number of individuals with the matching birthday. So Y can take on 0, 2, 3, 4, 5, all the way up to N. Notice there's no number 1. So if Y is the number of individuals with the matching birthday, it can be 0, no matches, but it can't be 1. If one person has a match, there has to be another person with that match, so there has to be at least 2, and then so forth. 3 people can have the same birthday, or 2 people can have the same birthday, and 3 other people have the same birthday but another day, and Y just counts those number of individuals. We're going to let PI be person I out of the sample of N, their birthday. So PI could be March 25 or November 10th, or etc. So as a quick example, if we have P1 equal to P2, comma, P3 equal to P4 equal to P5, it says these 2 people have the same birthday, these 3 people have the same birthday, but different birthdays, and so far there's 5 people that have a match. Okay, that's kind of the notation that I'm going to use for this video. And again, the goal is to find the probability of at least 1 match. So in our case, Y is greater than or equal to 2. And that's the common birthday problem. Okay, so the usual solution, and we're not going to discuss it much, is to find the probability that Y is greater than or equal to 2 is 1 minus the complement. But remember, there is no 1, so the complement is 0. So it's 1 minus probability Y equals 0. And then the probability that Y equals 0 is this. The total sample size is 365, and there's 23 people, so it's 365 raised to the 23rd power. Now the first person has 365 days to pick from. The next person only has 364 to pick from because they can't match. We're trying to find the probability of 0. The third person has 363 days, and so down to the 23rd person. You calculate this, and it's 0.507 is the probability. Okay, so that's the usual way to do it. We will calculate it like this. So the probability that Y is greater than or equal to 2, that's equal to the probability that Y is 2, plus probability Y is 3, plus all the way to the Y is equal to N. Now, you might ask, why the heck are we going to do that? And really, it's just an FYI and to practice with combinatorics. No other reason. This is absolutely not the most efficient way to do it, but if you want to learn how to or become better at combinations, permutations, then the video I think will be helpful. Okay, and we're gonna build up with this. So let's let N equal 1. So remember, Y goes from 0 to N, but can't be 1. So there's only one case for Y, And that's probability of no matches. And that makes sense. If you have one person, there's no way they can match because there's no other person to match from. So the probability that y is 0 is 1, 100%. And notationally, we're going to be a little tedious here because that's going to help in later cases. So out of the one person, we want 0 of them to match. And so that person has 365 days to pick from out of 365. So that's 1 times 1, which is 1. Now let's look at the 2 case. So there's a sample size of 2. So y can take on 0 and 2. And the whole sample space is the, probability y equals 2 plus probability y equals 0. So this actually should add to 1, right? Well, here, for this case, out of the 2 people, we were going to pick 2 to match, which means the probability that the 2 people's birthdays are equal. And then for this case, out of the 2 people, we were picking 0 to match, and we want the probability that they have different birthdays. Okay. So here, 2 choose 2 is 1. Now this first person has 365 days that they can be. And this person, after this one is chosen, they only have 1 day that they can be because they have to be the same. So this is the number of ways this can happen out of 365 squared because there's 2 people. Now this one, 2 choose 0 is 1. So this person has 365 days. This person has 364 days. So it's multiplied over that. And then to show this is 1, you can factor out a 365 and you're left with 1 plus 364, well, which is 365 squared, which is 1. Now for n equal 3 case, that means y is 0, 2, or 3. So y equal 3 plus y equal 2 plus y equal 0. This should sum to 1. So this first case is out of the 3 people, we want to pick 3 of them to match. That means the probability that each of their birthdays are the same. Here, we want to pick 3, out of the 3 people, pick 2 that we're going to match, which means, and then this is a specific case. So since they're all equally likely, this is the probability of 1 case. So the probability that the first 2 people have the same birthday and the third one is different. And then this is the number of ways, since they're all independent, that it can happen. This one, out of the 3 people, pick 0 to match, and then to find the probability that, they're different. Okay. So here we have 1. Now this person has 365 days that it can be. And then the next 2 only have 1 day because it has to match. So this is this probability. Probability y equals 3. Here we have 3 choose 2, which is 3. And then here the first person has 365 days to choose from. Second person only has 1 because it has to match. And then the third person has 364 days. And of course, this is over 365 cubed. Here, 3 choose 0 is 1. The first person has 365 days to choose from. The second has 364. The third has 363 because they can't match over that. Now, it's kind of fun to go through this and make sure that it equals 1. And this is the last time we'll do it, but I think it's a fun little exercise. So here there's 365 common in these 3, so let's factor it out. And then that leaves 1, 3 times 364, and that leaves 364 times 363. And of course, this is all over 365. Now here, notice there's 3 of these. So let's take one of those and add it with this and then leave the other 2 the same, right? So that's what we do here. So take one of those, add it, and we're left with 2, and here it just comes down, of course, divided by that. Now, over here, let's factor out a 364, right? And then that leaves 2 plus 363, which is 365. Well, now there's 365 common in both of those, so let's factor it out. and that leaves 365 squared times 1 plus 364, which is 365. So that's 365 cubed over 365 cubed, which is 1. Now for 4, and this is actually where it starts to get interesting. And then also, in my opinion, well, on the next page too, but this is the first case where you actually have to start thinking about all the possibilities. So here, let's let n equal 4. So y can take on 0, 2, 3, 4. So we can have the probability that 4 people match, 3 people, 2, and 1. And you'll see why there's a big gap here. Well, the probability that 4 people match, we can have all 4 have the same birthday, or 2 people have one birthday alike and the other 2 have another birthday but alike. So there's 4 people total. And so we have to think about each of those cases. So here we want 4 people. Out of the 4, we want 4 to match, and then we find that probability. This one, we have 4 people, choose 2 to match, and then the other 2, of course, by default will match. But if we'd have chosen these 2 in the 2, we're counting it too many times, so you have to divide by 2 factorial. And really, it's because there's symmetry here. We're over counting if we just go 4 choose 2, so we have to divide out the 2 factorial. And actually on the next page, when we get to y equals 6, when n equals 23, hopefully that you'll see this again. Now here, so these are for that. Now this one is out of the 4 people, choose 3 to match, and then the 4th one's different. Here, we want 4 people choose 2 to match, and then the other 2 are different. Here we're choosing 0 to match, and then the probability that they're all different. Okay, so now we come down. So here we have 1. Now this one has 365 days to pick from, but the other 3 only have 1 day because it has to match. So this is this probability. Over here, this is 3, and then this person has 365 days to match. They only have 1 day because they have to match. This person has 365 days. This person has 1. Over here, we have 4, and then we have this person has 365 days. The next 2 only have 1 day each because they have to match person 1, and then that person has 364 days. Here, that's 6, 365, and then the next person has 1, so, but 1 doesn't come into the product. That person has 364, that person has 363. So really that should be a 3. Here we have 4 choose 1 is 1. Here this person's 365, 364, 363, 362, and if you add up those, it equals 1. Now we're going to jump straight to the case where n equals 23. So y can take on the values of 0, 2 through 23. So let's first do y equal 20 or y equals 0. Now we can't consider them all together because it takes too much real estate. So we're going to consider them individually. So y equals 0 means out of the 23 people, we want 0 to match, and then we want to find the probability that they're all different. Well, that's a 1, and then the first one has 365 possibilities. The next one then only has 364, all the way, 23 times, it's 343. Over 365 raised to 23rd, and that's the 0.4927. And so 1 minus this, which is the probability that at least, that y is greater than or equal to 2, is 0.50, and that's what we did on the page 1. So for y equal 2, we want, out of the 23 people, we want 2 to match. So and this is a specific case since they're all independent. So person 1 and 2 match, and then all the rest different. Well, this right here is 11 times 23. You can do that. Then this person has 365 possibilities. The next person only has one because it has to match. Then 364, 363, all the way to 344. This is divided by 365 to the 23rd power, which is 0.36. Now let's look at, now I even start doing more shorthand calculations. The probability that y equals 3 means we're going to choose, out of the 23 people, choose 3 to match, right? So the first person has 365 ways. The next 2 people have to match, and then it's 364, and all the way down to 345. Divided by this, that's 0.007. Now, 4, 5, 6, yeah, we'll just keep going. And you'll see something here in a sec. So y equals 4. Remember, we can have 4 people with the same birthday, or we can have 2 of the same birthday and then 2 with another birthday but the same. So there's kind of 2 cases. So case 1 is, out of the 23 people, choose 4 that have the same birthday. So the first person, 365, the next 3 have to be that, so there's only one choice. And then the next 19 people have to have different birthdays, so it kind of goes down to 343. And now the divided by, I'm putting all over here. So all of this is divided by 365 raised to the 23rd. Now this is the interesting case. So remember that 2 people have the same birthday and another 2 have the same birthday but different than the first 2. So of the 23 people, choose 2. Of the 21 people remaining, choose 2 to equal. And then because it's symmetric, 2 and 2, then there's 2 factorial ways to arrange these. So we have to divide it out. Now here, the first person has 365 ways. And the next person has to match. Next person 364, next person has to match. Then all the others have to be different. So 363 all the way down to 345 divided by 365 raised to the 23rd power. That's 0.1109. And notice that we just went up, which is kind of interesting. With 5, we have that 5 could all have the same birthday, or it could be 2 with one birthday and 3 with another birthday. So those 2 possibilities. And as y increases, it actually gets a little crazier each time. So here, of the 23, choose 5. That means then the probability is 365 for the first person. The next 4 only have one choice because they all have to match. And then the next 18 people, go down, each have different number of days. Here, of the 23, choose 2. There's 21 left, so those 2 have the same birthday. Of the 21 left, pick 3 to have the same birthday. And then we do that probability. The first one is 365, next one has to match. The third person, there's 364 choices, but then the next 2 have to match. And then that's 363, 362, all the way down to 364. And that probability is 0.004. Okay. Now it even gets a little crazier. But notice that it's not symmetric. It's 2 and 3. Here it's 2 and 2. Whenever it's symmetric, you have to divide. You're counting it too many times, so you have to divide it out. So when we go to 6, okay, so how do we do this? So 6 people could have the same birthday, or it could be 2 have the same birthday and then 4 have the same but another day. Or it could be 3 have the same and 3. Or it could be 2, 2, and 2. All these are cases where 6 people have a match, right? So we have to consider those 4 cases individually. So this is when 6 have a match. So of the 23, pick 6 to match. And then this is the probability. It goes down to 348. Here, of the 23, pick 2 to match. Then of the 21 left, pick 4 to match. and then this is the probability. Now, granted, there's some ones in here that affect this, you know, like up here, there's ones, but really it ultimately it just goes down. So this is the probability that we have 2 and 4. Now we have to consider 3 and 3. So the probability of the 23, grab 3 to match. Of the 20 left, grab 3 to match. But since it's symmetric, we have to divide by 2 factorial. And then, you know, the first person has 365. The next 2 have to match. The fourth person is 364. Then the next 2 have to match. And then the others all have different birthdays. Now here, so 6 people are matches, but 2 have one birthday, 2 have another, and 2 have another. So this is the way to calculate it. Of 23 people, grab 2 to match. Of the 21 left, grab 2 to match. Of the 19 people, grab 2 to match. But look how symmetric that is. And what's the number of ways you could arrange those? 3 factorial. So you have to divide by 3 factorial. Now, the first person here has 365. The next one has 1. 364 ways for the third person. The fourth person has a 1 way because it has to match. And then you just keep going down. And this probability is 18. Now, the next 2, I only have 2 left. Y equals 7, Y equals 8. And I'm going to do shorthand just to help illustrate. So, and this is abusive notation, but I hope it makes the point of how to calculate it. So for Y equals 7, we could have 7 matches. So 7 and 0. I mean, everyone else doesn't match. Here we could have 2 people with 1 birthday, 5 with another, and everyone different. We could have 3 people with the same birthday, and 4 people have the same birthday, but a different birthday in the other 3. And here we could have 2, 2, and 3, right? And so you would calculate this very similar to what you do up here. The probability, I went ahead and did it, it's 0.0009 if you want to practice that on your own. Now for 8, I didn't calculate it, but here are the cases: 80, 26, 35, 44, 222. Now since this is symmetric, you're going to have to divide by 2 factorial. Divide by 2 factorial. 2, 2, 2, 2, that's 8. But you're going to have to divide by 1, 2, 3, 4 factorial here. 2, 3, 3, divide by 2 factorial, and calculate it. Well, anyway, I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.